All right, hi everybody. Posting this video on Wednesday. I know you guys don't have class, but just to kind of keep us in progression. So I was supposed to get through this on Tuesday, but ran out of time. So yesterday we had common types of forces. So your force weight, force normal, tension, and your two types of friction. Free body diagrams, FBD, are the things that we use in physics to kind of represent how these forces are acting on an object, kind of show up pictorially. Okay, so let's start by just giving that. Okay, so free body diagram, or FBD, zoom in a little bit, okay, is a pictorial, I think I spelled that wrong, representation of all the forces acting on, okay, it's just on a object. Okay, so it's a pictorial representation of all the forces acting on an object. Okay, that's it. Just forces on, not the forces an object does on something else, just the forces acting on that object. So here is the classic example I always go over. So let's say we got Bubba. Rush of bad luck, and his car died. So here's his car. Okay. And he is trying to push this car towards the right. Okay. So move car towards the right. Okay. So he applies a force to the right. So what a free body diagram does is it takes an object, so in this case a car, and it breaks it down into a simple shape. Okay, now you're thinking, okay, this car is a pretty simple shape as it is, but in physics, what we do is we break it down even simpler. So we always draw our surface. So this is the surface that the car is on. And then we draw the car in a simple shape. A box is a simple shape. So this car is now this box. All right? So that is what a free body diagram does. It takes this complex thing and breaks it down to something very simple, and then I always draw the surface it's on. Now I'm going to draw this again in a little more space. I'm going to draw it over here. Okay? So here's once again my surface, and here's my car. So the forces acting on this car. Well, first and foremost, okay, how we do this is we always start with a little dot. So this little dot represents kind of just where all of our forces propagate from. So we always draw a dot in the center, and we draw our forces radiating out from our dot. Okay? So Bubba is applying a force towards the right. So we say FP for force push. Okay. Well, that's not the only force acting on this car, though. Okay, this car, I know it's not stated, but probably has a mass to it, right? And we're on Earth, we're on a surface, so there's always going to be my weight, W. Remember, that's from W yesterday. Well, we're also on a surface. The car is on a flat road. Okay, because we're on a surface, we must have a normal force. The normal force is perpendicular to your surface. Perpendicular means creates a 90-degree angle. So we also have the force normal up. All right. And we're on a road. I'll be very explicit in questions, but we could probably also assume that this road's rough. So there's also going to be a kinetic friction force on it. And there you go. That's a free body diagram. It's taking this whole situation and it's showing all the forces acting on it. Okay? I go along with it. And this is really important because then we can do an extra step of solving. Okay? So let's take another situation. Let's say we Let's say Bubba's made himself a sign. Okay? So let's draw a free body diagram of this sign. Okay? So once again, we're going to look at just the sign itself and all the forces acting on it. Okay? So here's the sign. Let's see. Put my little dot in the middle. Okay. Well, I have a force weight going down. Why do I have force weight down? Because you're on Earth. It does not know where did I say this is in space. Now, the sign is not touching a surface. Okay, this sign is not touching a surface. So in this case, there's no force normal. But there's this little thing right here. Okay? Oops, my hand's covering. There's this little thing right here. That's probably some sort of cable, some wiring, whatever. Okay? So there is going to be some force upward. We call that tension. And that's it. Now, the reason why I need this upward thing right here is, if you think about Newton's second law, force is equal to mass times acceleration. If I stated that there's no force going up, there's just weight going down, what this free body diagram will represent is that this sign will be falling. Well, this sign isn't falling, it's kind of staying here. So we need something that balances these forces. Okay? One more example, and I'll kind of deep dive into this whole balancing of forces situation. So, Big Bubba. Bubba kicks this ball. Yeah, it's nice pictorial representation there. So Bubba kicks this ball once again towards the right. Okay, and there's going to say there's no friction. Okay, so free body diagram. Have my little ball. Dots in the middle. Force push. Weight. And because we're on a surface, force normal. Okay. Now the next step after we have this free body diagram is to now let's begin solving stuff out. What I mean by that is, okay, we have Newton's second law, F equals ma. But when I went over Newton's second law, I really went over it as summation of forces equals mass times the acceleration. Well, if we look, I have forces, normal and weight in the y, and force push in the x. Okay. So really, what we can think about this is two different things. I have summation of forces in the x equals ma, and summation of forces in the y equals ma. Okay? So really, this is where we're kind of the next step is. Where the summation, remember this fancy E sigma, is just all the forces acting in that axis, and then send them equal to Newton's second law. So let's think about this. For the x-axis, I just have one, force push. So I'm going to replace summation of force in the x and say Fp equals ma. So if I knew the mass of the ball, and I knew how fast it accelerated, I can find the force applied to that object. Okay? Well, let's go to the y-axis. This one's done. Let's go to the y-axis. Well, let's say that the ball stays on the ground. Okay? So like Bubba kicks it and it just rolls across the ground. Well, if it rolls across the ground, think about the y-axis. If it's rolling across the ground, that means the acceleration is 0. It's not moving vertical up or down. It's just going horizontal. So if that's the case, okay, let's now look at my forces. Force normal, positive, because it's pushing up, minus weight equals 0. Why is it equal to 0? Because the acceleration is equal to 0, mass cancels out. So what this can state is that my force normal is equal to my weight. Now, all this means is that these two forces are equal but opposite. Think about this. Your weight and your force normal are your Newton's third law. Remember, Newton's third law states for every action, there's an equal but opposite reaction. So for this ball, the action is that it has mass, and it therefore is applying a force of weight down onto the ground. The ground is then applying a reactionary force, or a force normal, up against the ball. So this makes it so that the ball stays on a level surface and doesn't break through a surface. So basically, if you ever like walk across a wooden plank, okay, and you hear the plank like bend, like you see the plank, feel the plank bend a little bit, okay, so that's your weight pulling down against the plank. The plank is now trying to push back up against you, okay? And this is how this whole thing works out. So that's free body diagrams. I'm going to do a deeper dive into this on Thursday to kind of do this more of the solving stuff. But that's all I got. You all have a good one. Thank you.